My name is Fernando Alvarado.
And my name is Ricardo Medina.
We are Blanketsburgo, and this is our final challenge presentation.
So basically, the Kalman filter works as a fusion of sensors. First, we use a mathematical sensor called odometry, and then we use the oracle detection to estimate the position. How this works basically is that first we estimate our position using odometry, and then when we detect an Naruko, we the Kalman filter acts as a ponderation between the two and decides which one makes the most sense and calculates the new position based on that.
So this is the node diagram of our project. We can see three important nodes: detector inador, localization, and bugueador inador.
Next is the reactive navigation algorithm, which we implemented bug 0. First, it tries to go to the point. When an obstacle is detected, then it goes to follow wall and follows the wall till the algorithm detects that there is no obstacle and it's cleared and it has a straight distance to the point, and then it gets on target.
So this is how the Aruco detector works. First, it gets the image from the camera of the puzzlebot, in this case, in the simulation. Then it finds an Aruco. If he detected an Aruco, then he calculates using OpenCV where the Aruco is in respect to the frame of the camera. Then we use a homogeneous transformation matrix to determine where the Aruco is in according to the position of the frame of the robot. Then we calculate the distance and the angle of the robot to the Aruco, and then we publish the distance, Aruco angle, and the Aruco ID.
Then how the localization node works is that first it gets the velocities from the encoders, then it predicts the position using odometry, then it decides if there has been an Aruco or not. If there hasn't, then it stays with the predicted position, and if not, it corrects with the position with the Kalman filter, and then it publishes the odometry and the transform. Okay, so first we start by creating a set point in the map. We created the set point uh, 0 on x and 1.25 on y.
The puzzle starts drawing, and then as he approaches Naruko, you can see the heading error. So it gets smaller. Here he turns in Naruko, so the covariance matrix and the covariance matrix gets bigger.
And right now it's following the wall to avoid the obstacles. There you can see it detects another Aruko and another, and the covariance gets smaller and smaller. And right there, it goes straight for the waypoint. As you can see, it got way bigger. And then it goes back to its starting point, which is -3 on x and -3 on y.
We can see here that the covariance matrix gets bigger because he's not seeing any Naruko and he's getting a lot of noise from the odometry.
But soon it will encounter more Arukos and will get even smaller, like there. Mhm. So for the performance, as you can see, when an Naruko gets detected, the error in distance goes way down. Here we graph the distance error and the time. So for our conclusions, the hardest part, the most challenging part, was implementing the Kalman filter because it deals with a lot of matrices and it's kind of very confusing math. Also, the Oracle detection was kind of a challenge because we have to thought a lot about the angle, which angle do we want it, and how to calculate it.
We can say that we correctly implemented the Kalman filter on the puzzlebot because, as we saw in the video, the ellipsoid gets smaller as the puzzlebot is in a rugo. This means that we can have a lot of precision with the position of the robot.